Hello, how is everyone doing this morning? Happy Monday. I found a new trick. I've got this new setup here where you can see me and you can see my slides. And yeah, so we're going to try this. So this is our lecture number 1 in the next unit, which is on simple harmonic motion. We're going to talk a little bit about things that move back and forth, things that vibrate, things that oscillate, go back and forth in this unit. So a couple things for you to write down in your notes. We're going to define this thing called simple harmonic motion. Simple harmonic motion is defined as any motion that repeats itself. So things that swing back and forth, things that go around in circles, things that are on a spring that oscillate and go back and forth and back and forth. And you can see here in this upper right corner here, examples are things like a mass on a spring. We assume that this surface here on the ground is a frictionless surface. And when we graph the position versus time, you'll notice that it forms this nice, perfect sine wave. We're going to talk a little bit about that here today. So let's take a look at one very key example here, which is of a simple pendulum. So a simple pendulum models this kind of simple harmonic motion going back and forth really well. So simple pendulum is basically just a mass on the end of a string, and it's just going to go back and forth and back and forth. The equilibrium point, the resting point, the point that it wants to be, the natural place, is right here in the middle, right here. And we define a couple terms here. We're going to define the term called a period with the letter T. Capital T is the time it takes for it to make one back and forth motion. So out and back is one period, and that's going to be measured in seconds. The frequency, oh, now my head is blocking that, so I'm going to duck here. Let's see, how do I do this? So the frequency is defined as the number of cycles per unit time, and that is measured in hertz. So when we were doing circular motion, these are the same formulas that we used last time. Frequency is equal to 1 divided by the period, or we could also say that period is equal to 1 divided by the frequency. And the last definition here, oh, now my head is really blocking it, is this definition of what we call the amplitude. And the amplitude is defined as the distance from that center point. So how far we are moving it, oh, I wish I could point that far, from the center to the outside point. So let's take a look at what it would look like if we graph this position. So if we graph just the horizontal position of this pendulum is moving back and forth and back and forth. When we graph that position versus time, it forms this perfect sine wave, back and forth. And so here it starts at 0, it's moving away in the forward direction, and then it starts swinging back. Now it's back at the center, moves to the left, now it's moving back to the right, keeps moving to the right, stops, and then now it's going back to the left, back to the center, now it's going to the right, and then the left, and then the right, and then the left. Now when we look at this motion here, we can determine what the frequency is. So the frequency is defined as the number of cycles per unit time. Here we have 1 cycle, 2 cycles, 3 cycles, and that looks like it takes 1 whole second for that to happen. So 3 cycles in 1 second time is defined as 3 hertz. The period, we said last time, period for 1 cycle is simply just 1 divided by the frequency. So 1 divided by the frequency is 1 divided by 3 hertz, or 0.333 seconds. And then the last, oh, I didn't put it here. If we were to look here, the amplitude of this motion would be from 0 to 0.25 meters would be the amplitude. So pendulums are really interesting. Pendulums were a thing that were studied by Galileo starting back in the early 1600s. And what was really interesting about pendulums back in the 1600s, there were no watches, there were no standard clocks, and in fact Galileo did a lot of his predictions just based off of the regularity of his own heartbeat. But he did a bunch of experiments and he looked at how pendulums worked. There's a couple things that we define when we look at pendulums. The thing that's hanging from the end of the string is what's called a bob. And the bob swings back and forth past its equilibrium point. That's the 0 point. The amplitude, sometimes measured as an angle, I sometimes just measure it as the horizontal distance here from the center, is that displacement from that equilibrium point. So if we were to look at this, what kind of things might Galileo have experimented with? And so things that he looked at were what might affect the periodicity, or the period of time it takes for this thing to swing back and forth. And so he looked at things like the mass, so the mass of the bob, the mass of the thing swinging, how far off of the center line that he started it, the length of that string, and then, maybe even how hard you push it. So what if you gave it a little push? Would that make a difference? And so there's a couple experiments, and I put a few animations here just to see, so we can see what happens here. So we have two pendulums here. The large one, the blue one, is a 1.5 kilogram mass. The red one is a 0.5 kilogram mass. Both have the same length of string. And you'll notice here that they both swing with the same period. So one of the really crazy things seems that like a heavier pendulum or heavier bob would swing at a different rate than a smaller one. But this experiment here shows that it doesn't matter. A different mass, same length, have the same periodicity. So what about if we started one with a larger amplitude? So here I started the red one with a bigger amplitude, so I swung it out much farther than the blue one. And you'll know that even though that the red one is starting farther out, they are both swinging back and forth with the exact same period. So that's curious, right? So amplitude seems to also not have an effect on the period of the pendulum. The last experiment that Galileo looked at was by changing the length of the pendulum. And now this is the one where we saw a change. And it's a little hard to watch this animation here, but if we watch it, we can notice that the blue, the longer one, seems to swing slower. It takes longer for it to swing than the short, the red one. And so length, the longer the length, the longer the period, right? So, and Galileo did a bunch of experiments and did a bunch of analysis and came up with this handy equation, which says that the period, t, is equal to 2 pi times the square root of L over g, where g is the acceleration due to gravity here on Earth. We assume that to be 9.8 meters per second squared. T, of course, is the period measured in seconds. That's the period for the pendulum to swing all the way from one side to the other and back. L is the length, and measured to the center of the mass, measured in meters. So let's take a look at how we might use this in a simulation. So one simulation, I'm going to show you this PhET simulation, and this will be one of the things you'll be doing in your homework. Alright, here we go. Alright, so when you go to the simulation, it'll look like this, and you're going to click on the intro, and it'll open up a window like this, and you can swing the pendulum out and let it go, and we can watch the time. Now you can use your own stopwatch, you can use your handy dandy cell phone, or there is also this button right here. We can click stopwatch, and it opens up a stopwatch that starts and stops. Now this is really hard because now I have to time it to see when it starts and stops. But if I pause this and click play, right, now when I click this play, so this play starts the stopwatch, this play starts the actual simulation. So I can go 1, and that gives me 1 full swing. Now you'll notice that I didn't get the full swing and I was a little bit off, so doing 10 full swings or something that's easily divisible is probably a good recommendation. I'm going to do, let's try changing this length to something like 0.4. I'm going to reset it. I'm going to move this to somewhere around 30 degrees as a starting point. And let's just play around with this and see if we can get the period for this. So I'm going to click play on the stopwatch, click here, and I'm going to count 10 full swings. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Well, that was off by a little bit there, so but I think it'll get averaged out. So 10 full swings was 13.16, so that means that 1.316 was the time for 1 swing, so 1.316. So let's remember that. 1.316, and the length was 0.4 meters. So if we were to take this equation here, t equals 2 pi times the square root of L over G. And we've now measured t, we know L. We want to find or calculate G. So I want to do the algebra first before I plug in the numbers. So let's just show you how we do that algebra. The first step is we're going to have to divide by 2 pi. So, oh, that didn't work. There we go. So first thing we're going to do is divide by 2 pi. So t divided by 2 pi now is equal to the square root of L over G. We want to get rid of that square root, so we're going to square both sides. So I'm going to square everything on the left side, and I'm going to square everything on the right side. So when I square everything on the left side, that's now t squared, and then I'm going to square this too. So the 2 pi squared becomes 4 pi squared. Pause there just to make sure that that sinks in. So squaring everything on the left side, so t squared, and then the 2 pi, that whole thing gets squared and becomes 4 pi squared, and the square root on the right hand side goes away. Now it's a little tricky. I want to get G by itself. So to get G by itself, what I want to do, oh, this is kind of fun, I can do this. To get G by itself, what we want to do first is I'm going to multiply G over to this side, right? And so if I multiply by G, now the L is all by itself on that side, G is over here, and now I can start moving this part of the fraction back over, right? So now the first thing I'm going to do is multiply by 4 pi squared. So multiply by 4 pi squared on both sides. That means that those parts cancel out. Go away, right? And now I get L times 4 pi squared on the right hand side, and I end up, oh, keep clicking on that link there. And then the last part is I'm going to divide both sides by t squared, and then you get this nice equation, which I had already put here on the slide, but G is equal to L times 4 pi squared over t squared. So now what we can do is we can use this. Let's see if I can do this on a sheet of paper. I'm going to do that derivation one more time. So we're going to show that t is equal to 2 pi times the square root of L divided by G, right? The first thing I'm going to do now is divide both sides by 2 pi. So divide by 2 pi, and then this divided by 2 pi. Those cancel out. And then I want to square both sides to get rid of that square root. So I get t divided by 2 pi, and I'm going to take the square of that is equal to square root of L over G. Right? I'm going to take the square of that as well. So what I end up getting is t squared divided by 4 pi squared is equal to L divided by G. Now this is where it's a little tricky. So I'm going to multiply by G on this side. Multiply by G here. Those cancel out. And now G is over here and L is over here. And so I want to move this bottom part over first. So I end up getting G times t squared is equal to L times 4 pi squared. And I just multiplied this on both sides. And the last thing we do is divide by t squared. Divided by t squared, right? And then we end up getting G is equal to L times 4 pi squared divided by t squared. And so in that simulation that we ran, we said that L was equal to 0.4 meters. We found that t was equal to 1.31 seconds. Right? And so let's see how accurate or how close this approximates. We think that G should be 9.8, 9.81, right? So we're going to try this. So G is equal to 0.4 meters times 4 pi squared divided by 1.31 seconds squared. Right? Oh, I ducked out of the camera there. And so here, 0.4 times 4 times 3.1415 squared divided by 1.31 squared equals 9.2. 9.2 equals 9.201 meters per second squared. And that's pretty close. I think, possibly more accurately clicking on the mouse or starting and stopping, maybe more trials. But that's not bad. And if I were to then calculate a percent error, I would say percent error is equal to this calculated minus my expected divided by my expected times 100. Right? So here I would say 9.201 minus 9.81 divided by 9.81 times 100. And if we were to try that, let's see what we end up getting. So 9.2 minus 9.81 equals this, divided by 9.81 this, times 100. And looks like I have 6.2%. So that's not bad. So 6.2% error. Right. So that's a quick demo on the simulation, and you should be set to do most of the homework problems for tomorrow. Go back to this. All right. So homework will be posted along with this video. Simple harmonic motion worksheet 1. Additional help and support. I'll be around and to help you all day today. as well as tomorrow. So as you give this a shot, shoot me an email. Let me know how it goes. If you get stuck, one of the problems will involve going to the PhET website and running that simulation, collecting some data. It's really important that you guys do this on your own. I'm not expecting you guys to get 9.81. And if you do, I will, well, good for you. But you'll notice that we just ran it, and I don't expect to see 9.81. So I do expect the numbers to vary, and if I see all the same answers, I will know that you guys are copying from each other. So give it a shot, play around with it, see how it works, and yeah. If you have questions, send me an email. Let me know how things go. We're going to try doing these kinds of videos Mondays and Wednesdays, and then I'll be around Tuesdays, Thursdays to help out with additional support. And then we'll throw together some quiz or some assessment for you guys on Friday. So, uh, yeah, this is fun. I hope this was useful, and I will see you all later. Bye bye.